Okay, so here we are looking at the last of the spectroscopic techniques that we'll look at before we move on to that last little bit on drug detection and analysis. So with this, we're looking at X-ray diffraction. So hopefully we can remember the radio waves that we've already looked at, infrared that we've already looked at, invisible light is part of the electromagnetic spectrum that we've already looked at. So we've looked at these parts here. Now we're actually looking at, so we've looked at radio, infrared and visible. Now we're looking at X-ray. So we're talking about much higher energy in this case, higher frequency and higher energy. Same sort of things that we use when if you go to have an X-ray at the doctor's. So we're looking at X-ray crystallography. So this is particularly suited and corresponds to the wavelengths of X-rays, looks at atomic distances. So from this we're looking at the position of atoms and we're looking at bond length. Okay, so again this is a type of spectroscopy, but it's crystallography. So we need our sample to be crystalline in order to look at it. So there's not much we need to know about this other than what we use diffraction, X-ray diffraction for, or X-ray crystallography for, and a little bit of information on how it's done. Essentially what we're looking at is crystalline solids. Now this isn't just ionics or metals that we've talked about. We can actually form crystals of a number of different things. Proteins, even covalent molecules, but we need them to be a solid at room temperature and crystallize them under very specific conditions. So just go with me on this, that under certain conditions we can usually get crystals of a large number of substances in the solid state. When we have high quality crystals, we can subject them to X-ray radiation. What this will do is it causes what we call a diffraction pattern. Okay, and this diffraction pattern gives us regular arrangements that can be interpreted and turned into the structure of the compound. Okay, so the better the quality of the crystal, the better the diffraction pattern we get. And we see also things like the synchrotron, using synchrotron beam lines and things like that allow us to get better images from smaller crystals. So with technology, we are seeing improvements in this. Essentially what happens is when we put the X-rays in, they interact with regions of electron density. Okay, so remembering that the larger the atom, the more electron dense it's going to be and things like this. So it's easier for us to see larger, more dense atoms. We don't typically tend to see things like hydrogen using this technique. What happens is we have waves. Okay, so we've got X-rays and X-rays act and behave as waves. When if we pass these through a sample, when they hit the same kind of thing, a bit like with the NMR, if they hit the same kind of environment, the waves that come out will be in phase. So with crystals, we get a highly repetitive structure. So where they're interacting with something, we will see that being in phase. So they will add constructively. So if they're in phase, they add constructively, and the overall result is amplified. Okay, so where we have the same sort of interaction happening, which produces constructive wave types, we will see high intensity X-rays. When they're out of phase, so they're not interacting in a regular pattern, what happens is we get destructive interference, they cancel each other out, and we get low intensity X-rays. This pattern of high intensity and low intensity can then be mapped. So the X-rays are found to be in phase when they enter the crystal, then are scattered at different angles and distances due to their interaction with the electrons, as we see with this diagram here. The diffraction pattern depends on the angle of incidence that it goes in, the wavelength of the X-rays used, and the distance between the atoms and their orientation. Okay, so because it's dependent on their distance, okay, we can see a diffraction pattern, which is what is over here to the right. And crystallographers can interpret this data by taking measurements and finding out the actual position of the atoms. what this will generate is what we call an electron density map. So we can see here, these regions here are where we see electron density. Okay, these little fuzzy bits around here are possibly hydrogens, but we've got some definite strong signals here. We don't tend to see hydrogen because it doesn't have a very high electron density, so hydrogens are added later by the crystallographers following typical bonding patterns. This becomes like a contour map that you may have seen with maps, or if you're doing cadets, the idea of contour lines and things like that. So we have these regions here that are high density, and that tells us that there's something there and approximately the size. We then get the bond lengths by going from the center of one to the center of the other. So this here, because they're close together, this would indicate that there is a bond here. So have a go, pause the video, and see if you can draw the possible structure of what this is, thinking that each sphere here represents an atom. If they're close to each other like this, we're going to have a bond, so we'd have a bond here, and see if you can draw what you think the structure would be, and come back and see what it is. Okay, hopefully you had a look and you came up with this fused ring structure here where we have 3 benzenes in a row. These are actually, you can have a look here, these look like ring structures that we see with carbon, okay, and then this is actually a structure that we see here. So you can see it's not an exact picture. Crystallographers do a lot of training to be able to figure out exactly what's going on. So the bond lengths and bond angles can be determined from this information. Okay, so we get the electron density map, we can look at the exact bond lengths and bond angles, which is something that we don't see with other forms of spectroscopy. So we can only get this because in a crystal, remember these atoms are not moving a lot, they're just vibrating in space, so we can actually see what they look like when they're fixed in space. So if we look at this, this is our simplified electron density map of a compound. Okay, we can see we've got a ring structure here again, and then we've got another bond coming out here. See if you can identify the compound, okay, from its bond length data. Remember, you have bond lengths in your data booklet. And explain why all the atoms may not be shown in the electron density map, and deduce the degree of hydrogen deficiency of the compound. Again, I'll ask you to pause the video, have a go at answering these questions, and then come back and see what we have for the answers. Hopefully you have had a look at this and you've come up with a solution. I'm not going to give you the answer quite yet. I want to talk to you about what we use this information for and how it's been quite powerful for us to be able to get information as chemists. So the reason that we want to be able to do this and do what you're doing now in terms of predicting what the structure is and working out what's going on is crystallographers have used these electron density maps to be able to produce maps of proteins and of molecules. So if you look at this one on the left here, this is actually a crystal structure of a protein that has a surface map over the top of it with a drug bound into the receptor. So if we can get crystals of biological proteins and enzymes with drugs bound to them, it gives a better indication to us of how they're working, and perhaps if it's a natural substrate, how we might design a drug to be able to fit into that area. So crystal structure has been very powerful in that way. The other one is to actually get crystal structures of complex molecules. If we can get a good enough quality crystal, we can actually then use this to find the exact bond angles, bond lengths, and therefore determine the stereochemistry. So determining if things are above or below the ring, or the three-dimensional stereochemistry of our enantiomers. So this allows us, if we can crystallize a natural product, to have a look at that stereochemistry, figure out if there are enantiomers, and therefore be able to test individual enantiomers if we know of their existence, so we can test those for drugs as well. So this is one of the few techniques where we can actually see the atoms, well, see is a relative term, but look at the atoms relative to each other in space and get actual pictures of where they're located. We can infer a lot of that from NMR and spectroscopy, but this actually gives us bond angles, which is the only technique that does that. Okay, so this is our answer. So if you had a look, we had the 6 spheres and regions around here, all of the same size. This one was of a similar size. And again, looking at your bond angle data, you should have been able to deduce that it was a carbon-carbon bond here. Remembering that the bonds in benzene were going to be smaller because they have that 1.5 bond order. So the hydrogen atoms are the ones that we're not seeing because they have a low electron density, so they don't appear. And hopefully you can remember that the bond order of benzene is actually 4, or you can calculate it, and this is not going to change our bond order at all because it's fully saturated. These are some textbook questions that I recommend that you have a look at and go through their solutions, which you have as well. Okay, this is the only type of thing that we're going to be asked in terms of X-ray diffraction. You don't need to know much more than this about it. Okay, so just being able to know what the technique is that we use it for bond angle data of pretty much anything, that we select a particular wavelength of X-rays, okay, using a monochromator, which we've talked about in spectroscopy before, the low electron density of hydrogen, and being able to use crystals because of the regular arrangement, therefore getting an ordered diffraction pattern for interpretation. This is a quick summary. Basically, we cannot get molecular formula. We cannot get anything, pretty much. It locates an atom in space and gives an idea of the crystal structure, but it doesn't tell us what atoms are present. We kind of need a microanalysis and other things like that to be able to tell us that. All we get is some little spheres. So we need to be able to use other information to get that interpretation. It will tell us stereochemistry and bond length, therefore the distance between atoms. It tells us nothing, however, about the presence of lone pairs or electronegativity, and doesn't give us any information on the formal charge. And formal charge we'll talk more about when we do HL bonding. Okay, so this is a particularly important thing to remember, in that because it's an electron density map, hydrogen doesn't have a large electron cloud, so it's not detected, and crystallographers therefore put that in afterwards. So hopefully that made a little bit of sense, remembering that this is one that we don't have to be able to interpret. We just need to be able to understand what this technique is used for and how the spectrum are obtained.